Example 7.6. In this example, we evaluate how an electrical circuitry is written into a photovoltaic panel by depositing a small stream of droplets of ink, which come from a thermal inkjet printer. The drops are initially at a temperature of 200 Celsius and is desired that they hit the panel at 50 Celsius. The air that is surrounding the drops are at 25 Celsius. And when the drops are ejected from the print head, they have a terminal velocity. It is necessary to determine the extent of distance between the printer and the panel. The assumptions for this problem is that the properties remain constant for the air and the ink. We have negligible radiation and there is no temperature variation within the droplets. And we evaluate the drag coefficient by Stokes law, since it's considered to have a very low value of Reynolds number. The first step in the analysis is to determine the velocity at which the droplets are moving. The velocity is, in this case, is equal to the terminal velocity, which is determined when all the forces acting on the system are equal to 0. The three forces acting on this system are going to be the weight, the buoyancy force, and the drag force. For the shape of the sphere, we're going to use a volume equal to pi d cubed divided by 6, and the surface area that we're going to use is going to be pi d squared divided by 4. The weight of the droplets is going to be equal to the density of the ink or the droplet times the gravity times the volume. The buoyancy force is going to be the density of air, gravity, and the volume of the sphere. The drag force is going to be equal to the drag coefficient times density of the air, velocity, divided by 2 times the surface area. Since we assume that the problem uses a Stokes law, we could have that the drag coefficient is equal to 24 divided by the Reynolds number. Using all this information, we could find that the velocity or the terminal velocity is going to be equal to the diameter square, g, the differences between the fluid density and the air density, divided by 18 kinematic viscosity times the air density. Using this information, we find that the velocity is equal to 0.19 meters per second. Now that we have the velocity, we could calculate the Reynolds number to find out whether or not the Stokes approach was valid. We find that the Reynolds number for this particular case is equal to 0.506, which is small enough so that the Stokes law approximation is valid. The next step in the analysis is to determine the value of the convection coefficient. For the approximation of the Nusselt number, we're going to use the Runge and Marshall approximation for free-falling spheres. The Nusselt number then is defined as 2 plus 0.6 Reynolds number to the 1/2 Prandtl number to the 1/3. With the information given in this problem, the Nusselt number is equal to 2.44. Using this Nusselt number, we could find that the average convection coefficient is equal to 1160 watts per meter square. Okay. The goal of the problem is to determine the length between the printer head and the panel. We know that the velocity of the spheres is constant, therefore we could relate the velocity to the distance between the printer and the panel and the time that it takes to travel from one location to the next. The time is going to be calculated using the differences between temperature. The sphere starts with an initial temperature of 200 Celsius and is intended to finish with a temperature of 50 Celsius. Assuming that there is no internal change in the sphere temperature distribution, we're allowed to use the LCM approach to calculate the time that it takes to go from this temperature to this one. Using the LCM evaluation for time, we find that this is equal to the density of the droplet, the volume of the droplet, the heat capacity of the droplet, divided by the average convection coefficient, the surface area, and the natural log of the theta I divided by theta F. Remember that theta I is simply Ti minus T infinity, and theta F is simply Tf minus T infinity. With the information provided, we could find that the time is going to be equal to 0.03 seconds. Since we know the value of the velocity, we could calculate that the length between the printer and the panel is going to be equal to 5.6 times 10 to the negative 3 meters, or 5.6 millimeters. Please go back and double check the calculations. Make sure that you understand why we use the relationship for the Nusselt number, and be able to double check the results.